Good morning. We are going to be doing chapter 4 homework. And the first one, 4.1.1, we're going to be looking for values that are not valid numbers for a probability. In your exercise, it could actually be asking you for numbers or values that are valid numbers, so just make sure you're paying attention to this not. If it says not, make sure you're indicating that in your answers. Okay, 0, that's a valid number for a probability. The only things that we can't have as that are invalid are negatives or ones that are over 1. Okay, so if you see a improper fraction, so ones that are not valid are going to be any ones that are negative and any ones that are improper fractions here. So I'm seeing this 264, this negative, and this improper fraction. Okay, so the other ones, it looks like, are valid. Again, just be careful that you're paying attention to whether it says not. In my case, it says ones that are not valid, so invalid ones, but in your case, it may say ones that are valid. So those would be the complement. What is the probability of randomly selecting an ace from a standard 52 card deck? Well, we know there's 52 cards in a deck, and 4 of those are aces. So what we could do there, let me bring this over. And I can post, I will have something posted online relative to the cards. Here, all we're saying is there's 4 aces. You divide that by 52, so the probability of selecting an ace is 0.72, 3 decimal places, 0.77. Okay. If it had said a red ace, only 2 of the aces are red, so that would be just a matter of changing this numerator to 2. Okay. A customer survey asks respondents to indicate their highest level of education, and the only choices are high school, college, and other. Okay, so this is actually an example of a complement, because we know that all together the respondents have to add up to 100%, right? And we know that 24 and 55 indicated high school and college respectively. So 0.24, I'll just put plus 0.24, 0.55, and this has to be a value that we're looking for. But we know that the total is going to be 100%. So how do we get that missing value? Take the complement, right? Equals 1 minus this plus this. So 21%. Now here it says 0.21 because I was putting it in terms of probability, and that's going to correspond to 21%. So converting that to a percentage. If I want Excel to report it in terms of a percentage, I can actually just indicate that here, and that is underneath the number category here. The default here is just going to be number. It tends to be fairly smart, but it doesn't. Excel doesn't necessarily know if you want to report it in terms of percentage or not. All right, we're going to create a contingency table here. I'm just going to create a new one. I can grab this and put it in a clipboard. Done. Okay, so the probability, and the first thing I'm actually going to do when I create this is just sum up these values. So I get my marginal totals and the overall. Oops, sorry. Bring this all the way down. Okay, so I have 50 overall. And in order to figure out what the B or the probability of B or C is, essentially what I have to do is add those up. The probability of B is 10 or C is 12. And so that is actually going to just be equal to 3 plus 12, because this, all of these are B and all of these are C. Now what's happening here is we're counting this value twice. Okay, so what I end up having to do is, after I've summed those up, is subtract that out. Okay, and then I actually take this value and I divide it by 50, the total. Okay, so it looks like to get either B or C is going to be 50%. Same thing for B or D. I'm going to add up those marginal totals and then subtract out this simple cell. That's what we call the simple probability. So this plus this, and then subtract out that. And I could actually do this all in one step if I wanted to. Divided by this. Looks like that's going to be 0.9. D or D. So 90%. A or E. The total of A. The total of E. Subtracting out that redundancy and dividing by the total is 0.74. Now here they're asking the probability of A or B. And actually A or B, the total is going to be 50. Okay, so it's 100% that we're either going to get event A or event B. So we can just put 1 there. Likewise, if they ask you the probability of getting C or D or E, that also is going to be 100%. Okay, so we've got another contingency table for our next problem. And again, yours may not be in this exact same order, but the problems are all the same across all the homeworks. Okay, so the probability of getting an event A, given that we have event C. Okay, so what I'm actually going to show you here, and you could have done this also before. After I sum these all up, if you want, you can actually get the probabilities just by dividing by the total here. So these are the actual probabilities. I'm going to do that for this next one as well. And in that case, at the end, you wouldn't necessarily have to divide by 50 because you already have your totals included in the problem, or in the probability. Okay, so this is conditional probability, and we're really only interested in this event C, and of those event C's, how many are event A's. So when we're looking at conditional probabilities, we're saying conditional on the fact that it's event C, what's the probability that it will also be event A? So another way to think about that is that the denominator is going to be the total value of C, so 50. So we're actually just taking 11 and dividing it by 50. Another way, again, as I showed you before, this is actually kind of redundant, but all of these, because they're divided by 100, are just going to be the probabilities like 0.11, 0.39, 0.50, so on and so forth. So to get this conditional probability, I'm just going to take this, divide it by this, and it's that 0.22 that it's giving me. Email. Okay. Now let's determine the probability of C given A. Okay, so this is the probability of A given C. And the probability of C given A. Now what we're going to actually do is we're really only interested in this particular column. And of these event A's, how many are event C's? Is that 11? So 11 is now going to be divided by the total number of event A values, so 0.24. The probability of B given E, probability of B given E is going to be, given E, how many are B's? So this divided by this, 0.12. And the probability of E given B all of these event B's, how many of those are E's? Equals E divided by B. Excuse me. 0.505. Okay. Here we're actually able to do the same thing. Bayes' theorem is actually what we just employed. So we're going to do something very similar here, where we are going to copy, and my sheet 1, I think I've got it, such that the probability of B given D. Okay, let's first grab our sums. Sum. Okay. There we go. And the probability of B given D. Okay, so I'm going to show you how to do this a couple different ways. To actually use Bayes' theorem, essentially what we would do is take the probability of, in this case, let me just pull this out here. I have my to do this one. We've got our, okay, so we have our probability of B given D. So in order to get this to populate, we could do it a couple different ways. Again, if we're only interested in D, of those, how many are B's? It's going to be this divided by this. Oops, yes, that's fine. I forgot to close my parentheses out. But another way that you could actually do this is take the probability of B, multiply it by the probability of D given B. Okay, so sort of like the opposite. And that's going to be your numerator, the product of these two things. And then the probability of, in this case, it would be A over the probability of D, oops, D given A. What do you think about that? Okay, so the probability of B is this divided by this. Yes, that's fine. The probability of D given B, D given B, given this divided by this. Okay. The probability of A is this divided by 100, and the probability of D given A, this divided by this. Okay. So what I'm going to show you here is that if I use this as my numerator, the product of these two things, okay, I'll put it like this. This is the numerator in Bayes' theorem. The denominator is going to be this product plus this product. Okay, so we already know this is 0.27 in the numerator. So we could say this plus this times this as our denominator. Okay, so this is the denominator. So another way to get the probability of B given D is given through this formula. The probability of B times the probability of D given B over this plus the probability of A times the probability of A given, or sorry, D given A. As a fraction, okay? So you take this product and you divide it into the sum of these products. Again, the shortcut being you can just take the fraction of all of the, given that it's D, what is it, the probability of it being B, so 27 divided by 38. But it's important to know sort of the math behind the longhand version as well. And we'll see that. So here, let's do 0.71 to 2 decimal places. Okay, great. Okay, let's consider the following two events that involve flipping a single coin and rolling a 6-sided die. All right, so the probability that the coin comes up tails and rolling a 4 with a die. Are these events mutually exclusive? They're not mutually exclusive. I can, an example of a mutually exclusive event would be if event A is the coin comes up tails and event B is the coin comes up heads. Those two events can't occur simultaneously. So in this case, the events are not mutually exclusive. It can occur at the same time as rolling a 4. Are these two events independent? So why or why not? If I roll a tail, does that affect what I'm going to roll with my die? So if I throw a toss, if I toss the coin, does it have any effect or bearing on what's happening with the die? No. So they're completely independent. It does not influence the other. Okay, so here we've got a local car dealership that has 41 used company A, B, and C cars that can be classified as either cars or trucks. So the following data are available, and we have to complete the rest of the problem. So I'm actually going to set this up so they've given me the total. I'm actually setting up a contingency table here. So I'm going to have company A, company B, company C, and it can be either cars or trucks. It doesn't matter what you have as rows or columns. I know that the total number here is going to be 41, and that there's a total of 30 cars. So we can deduce that the remaining are going to be trucks, okay? So this minus this. And companies, the following data, okay, so 14 are A, 14, 16. So again, we can deduce what the number of C is going to be. Again, employing that complement rule. 3 vehicles are both company C and trucks. So C, trucks, this is 3. So I know this has got to be 8. And 15 vehicles are both company B and cars. So this is 15. This is 1. And we know that this has got to be 7. And this is going to be 7. Okay. So what is the probability that a randomly selected vehicle is company C? So of all the cars and trucks, 11 out of 41 are company C. So we just divide the total of company C into the overall total to get this 0.268. What's the probability that a randomly selected vehicle is a truck? Total trucks are 11. Divide that into 41. Same value. And what's the probability that a randomly selected vehicle is either company B or a car? So remember, this is similar to saying probability that it is B or car. So we're going to have some overlap here in the ones that are cars and from company B. So we're going to sum up all of the B's and all of the cars and subtract out this and divide this entire thing by the total. Oops. Okay. 0.756. 3 decimal places. Okay. And the probability that it is a company A truck. So company A truck, there's only 7. Now it's not a conditional probability, it's an overall probability of being a truck from company A. So that's actually just the same as saying equals 7 divided by the overall total. So about 17%, 0.171. And the probability that it's a company C vehicle, given that it's a car. Okay, so given that it's a car, we're only dealing with 30 cars here. So how many of those given cars are from company C? Is going to be 8 divided by the total number of cars. So again, the way that you would write this, probability of C given that it's a car. 0.267. You will get points off for not rounding correctly. And that can be frustrating, but you just have to round. It can make a huge difference in life to round improperly. What's the probability that a randomly selected vehicle is a truck given its company B? Okay, so another thing, B truck given B. So given that it's B, what's the probability that it's a truck? This divided by this. 0.063. Okay, now this is giving us a sort of decision tree for these different events, and I can already kind of take a look here and say, I know it's going to be this one because this one actually doesn't even account for the probability of company C. So it only splits into 2, whereas if I was to split by the company, I'd need to split it into 3 nodes, or to 3 sort of different lines. So I know it's this one because if I split by the type of vehicle, there's only 2 types of vehicles I'm interested in, trucks and cars. So here this is the correct one. What I need to do now is put in the probability for all of these values. The way that I'm going to do that quickly is just divide everything in the contingency table that I've created by the total. Okay, so here I'm just going to say divided by, I'm just going to hard code 41. I could absolutely reference this. I'll do that too. I could divide it by 41, or I could absolutely reference that. And drag this and drag it over. So that's going to be that. Now I'm going to have to put the probability of a truck here. The probability of being a truck, so let me just write these in here. My probability, these are my subtotals and the total. So the probability of being a truck is 0.268. Not sure how many decimal places to 3 decimal places, 0.268. And 1, it's saying the probability of a truck and A. So the probability of being a truck and A is this, right? It's a truck and A. 0.171, let's say. 2 is a truck and B. Okay, so truck and B is this 0.02439, 0.024, and 3 is a truck and C. So truck and C is this 0.073. Okay, now the probability of a car is 0.732, about, if I'm rounding to 3 decimal places. Now note, all of these are going to sum up to your value of the probability of a truck, because all of these are the probability of being a truck. They're just from different companies. So all of these values should sum up to be the probability of a car overall. All right, so the probability of 4 being a car from company A, car from company A is going to be this 0.171. 5, car from company B, 0.366, and car and company C is 0.195. Okay, so the first part requires that you understand how to split the tree initially. If this one had a probability of company C, then it would, obviously work as well, as long as all of the choices are represented here. Not all the choices in our contingency table are represented in this diagram. So we know it's this diagram, and the 1, 2, 3, 4, 5, 6 corresponding probabilities are going to be corresponding to that which we see in our probability table, our contingency table. Okay, at a local restaurant, 28% of the customers order takeout. So the probability of ordering takeout is 0.28. 11% order takeout and choose a hamburger. Takeout and hamburger is 0.11. So what we're interested in here, they're asking, is the probability of ordering a hamburger given that we are ordering takeout. The way that we do this is this, sorry, the probability of taking out and ordering a hamburger divided by this. Okay, perfect. And that's because in order to get this, it's simply the probability of t divided by the probability of t and h. Same thing. Okay. The table to the right for number 10 shows the number of people in thousands in a country without health insurance in a certain year. Let's grab this data. Okay. We're going to sum this up. It's not giving us the sum, so let's sum this up first. And sum this up. So again, the way that you're reading this is that there's about 75,066 people that are under 18 years of age in this particular country. Okay, so what percentage of the country's population in the year did not have health insurance and was between the ages of 18 to 24? Okay, or I'm sorry, when I said that I meant under 18. All right, so the percentage that does not have health insurance, so is uninsured, and was between the ages of 18 to 24 is going to be this cell. We have to divide this by the total. Okay, so probability or percentage, uninsured and 18 to 24 is this divided by this. So percentage here, I'm going to indicate just hitting the percentage. It wants me to round the 2 decimal places. Let's put that like this, 2.75. Okay, so all I did here is I changed my number to a percentage and I increased the number of decimal places. Did not have health insurance or was between the ages of 25 to 34. Okay, so the probability of uninsured or 25 to 34. Again, what we're going to need to do here is take the total of 25 to 34, add in the overall uninsured, subtract out the overlap, and then divide by the total, overall total. Here again, change it to a percentage, and the decimal places are already at 2. Percentage of the country's population that did have health insurance given that they were 65 years or older. So the probability of being insured given 65 and above. So actually the only row that we're interested in here is right here, and of those 38,977, how many had health insurance? Dividing by this, okay? And percentage, 2 decimal places, 98.19. Do age group and health insurance appear to be independent or dependent events? Let's define event A as a person who is 45 to 64 years old, and event B as the person is insured. What conclusions can be drawn? Okay, so what we have to actually do here is they're giving us a bit of a hint. To check the probability of A, so define event A as a person who's 45 to 64 years old. So the probability of event A of 45 to 64 is this 81 divided by the total. Okay, so that's just the probability of being in that age group. The probability of, and here they're saying A given B. So the probability of being 45 to 64 years old, given that they are insured. Okay, so given that they are insured here, how many of these 254,953 people are in that age bracket? So this value. So in this case, probability of being I'll just put A given B here. So given B is the person is insured, okay? And so here it's going to be equals given that they're insured, this divided by this. So here these are roughly equitable, meaning that people in the population that are ages 45 to 64 is about 26% of the population is represented in that age bracket. Of those insured, it's about the same, 26%. So we would say that these particular events are independent because they are roughly equitable. Okay. Now note, they're not exactly the same. Note that that double tilde is like an approximation. So they don't have to necessarily be the identical value, but about 0.26 is pretty good in terms of equity. Okay, so 31% of customers who purchase products from an e-commerce site had orders exceeding 110. If 18% of customers have orders exceeding 110 and also pay with the e-commerce site sponsored credit card, determine the probability a customer who exceeds 110 will pay with the sponsored credit card. Okay, let's figure out what they're asking here. They're telling us that the probability of exceeding 110 is 23:1, and the probability of exceeding and customer, I'll just say card, is 0.18. Determine the probability of E exceeding 110 okay, actually this is saying determine the probability that a customer whose order exceeds 110, so given that it's 110, how they pay with the card. So given that it is exceeding 110, okay? So again, this is an example of the probability of, in this case, card given E equal to the probability of E and card divided by the probability of just exceeding. Oops. So that's simply just going to be the probability of E and the card is this, and we're dividing by the probability of it exceeding this. And so this should be about 0.581, 3 decimal places. Great. Okay, now we've got another contingency table here, and we're going to calculate some of these probabilities. Again, you should be indexing the numbers here corresponding to, you know, the homework numbers, because you can use this workbook in your quizzes and your exams. So we pull these questions, some of these questions could be appear again in your quizzes or in your exam. So however you want to index them, you might say, you know, chapter 4 point gender college or something like that, or just 4.2.27. Okay, let's grab the sums quickly here. Sum. I will not bore you with my songs here. I do that enough with my son. Okay, determine the probability of selecting a female. Alright, so probability female is simply going to be the total number of females divided by the total. 3 decimal places. And determine the probability of selecting a student that is 22 to 24 years old. Be 22 to 24 equals 22 to 24 total. This divided by the total. Okay, 0.17. Where is it? 6. Check it. Good. 35 years or older, a female. Okay, so probability of being female and over 35. Okay, so 35 years or older and female is going to be this particular value. Okay, because what they're saying is she's 35, she's a woman. This is the number of people that fall into that category. Let's divide that by our total. So about 20% of the sample. Excuse me, I have to edit that out. I don't want anyone seeing my sneeze face. Alright, determine the probability of selecting either a student who's a woman or is 25 to 29 years old. Okay, so the probability of being female or 25 to 29. Okay, so probability of being female is this, plus 25 to 29 is this. Remember, what do we have to do here? Subtract out that overlap. Good. And divide by the overall total. Okay, so about 0.64. And the probability of selecting a man given that he is 22 to 24. Okay, so this is going to be given that they're 22 to 24 years old. How many of those 1,230 are men? This divided by this. So about 0.439. Right, recall that when it says probability, it has to be between 0 and 1. When it asks for the percentage, you just multiply the probability by 100. Determine the probability, given that they are a man, is 30 to 34. Okay, so probability 30 to 34, given man. These don't necessarily, you know, have to be in here. They're not necessarily asking. It's nice to understand how to represent them, though, numerically, or I guess you could say from a probability standpoint. So given that they are male, this column, what's the probability of them being 30 to 34 years old? That's fine. 0.54. Okay. Ooh, the DVD one. Okay. So a major video distributor purchases blank DVDs from 2 sources. Retailer A is actually giving us 0.73, and retailer B gives us 0.27. Okay. So I'm going to actually change this a little bit, because I'm going to call the retailer the event A. So event A is the retailer. So essentially what retailer A is going to be is event A1, and retailer B is going to be A2. And this is just going to be consistent with the formulas that we've been using in lecture. Okay, so event B then is whether or not it's defective or not. Okay. So historically, 3% of the DVDs purchased from retailer A have been defective, whereas 4% of the DVDs purchased from retailer B have been defective. And now a randomly selected DVD is found to be defective. So we have to find the probability that that DVD came from retailer A. So the probability of A1 is 0.73. The probability of A2 is 0.27. Now the probability of, it says from retailer A have been defective. So it's defective given that it's from retailer A, and that is 0.03. And the probability of it being defective given that it's from retailer B is around 4%. Okay? Now we have to figure out what the probability is that it came from retailer A. Okay? So what we can do here is retailer A, again, recall that that is retailer A1. So the probability of event A1 times the probability of B given A1. In this case, multiply that. Alright, and this is our numerator. This is just a use of Bayes' theorem here. We're going to use that same numerator, but then we have to add in, recall, the probability of A2 times the probability of it being A given A2. Okay, so this is this, and here we're just going to add it. I'm going to have to actually go through and do this. This is, I'm just trying to show it to you, what it would look like from like a fractional standpoint. So this is the numerator, and this is the denominator. Okay, so all we have to do here, we actually have all this information. Probability of A1 times the probability of B given A1 is here, right? And then I have the same value plus the probability of A2 times the probability of B given A2. Okay, so all we're going to do here, this is our numerator, this is our denominator. We could have combined this all in one, but I think for instructional purposes it makes sense to do it this way. To 3 decimal places then, it's going to be 0.670. All right? So given all of the information that we have about where we're getting the DVDs and the probability of them being defective, given that it's from those respective DVD retailers, the probability, if we were to just randomly find a DVD to be defective, using Bayes' theorem, the probability of it being from retailer A is about 0.67 or 67%. Okay. And the last one, if the order of objects is important. So order here, we're thinking about combinations and permutations. So if the order is important, it's going to be permutation. So how many ways can 7 objects be selected for at a time? So if we put permutation here, it's going to say the number and the number chosen. So we have 7 objects, and the numbers chosen is going to be 4. So 7 and 4. And there's 840 different ways. Fantastic. I like to end on that note. Okay, great job on homework 4, making sure that you are keeping your Excel workbooks nice and tidy and labeled correctly, however you want to label them, to help you reference them during the quizzes and exams is the right way. So, good